So welcome back. So today we will learn about subspace and linear independence. So if a vector V is a linear vector space defined with two operations, the vector addition and the scalar multiplication, as I have mentioned in my last video. So if I have a new set V which is a subset of new set W which is a subset of V, and it is also defined with the same properties, the same two operations, the vector addition and the scalar multiplication, and the objects in W follow some properties, then the set V can also be a vector space. So the first property that the objects in the set V have to follow is that there must be a zero vector that exists in W. The second property is that the addition of two vectors which are present in W results in a vector which is already present in W. The third one is that the scalar multiplication of a vector present in, and the last one is that the additive inverse of any vector in W must be present in W. So I have taken an example for this. So this is example x1, x2, 0. So let me check if all the properties are being satisfied or not here. So if I substitute x1 and x2 by 0 and 0, then I can check that it is existing in W. So it is satisfied. That is, the zero vector is lying inside the set V, the set W. The second property is that the addition of two vectors lying in W must result in a vector which is already present in W. So let me substitute this x1 and x2 by some values, by some real values, as x1 and x2 are real. So if I substitute x1 by 1 and x2 by 2, and let me call it as u, and also a new vector, let me substitute x1 by 2, x2 by 1, then it results in it is 3, 3, 0. So I can see that 3, 3, 0 is also present in W, as it is not violating any law. Actually, what we have done here, we have just set the third coordinate of W as 0. So until we are not violating this 0, then we are going to satisfy all the properties. That is, this is also lying inside the set W, and this is being also satisfied. The third property is that the scalar multiplication of any vector present in W must lie inside W. So let me take k as 2 and let me multiply it with u. So this is u, 1, 2, 0. So I am getting 2, 4, 0. So also this is lying inside W. So this property is also being satisfied. So if I have to check a given set of vectors present in W are so if I have to check if W is a subspace or not, I have to check only the first three properties. The rest are being satisfied, as W is itself a set lying inside a vector space V. So what I have to do? I have to just check the three properties. The first three properties, that is a zero vector, the addition of two vectors, and the scalar multiplication. So by this way, I am going to check whether a set is forming a subspace or not. So let us learn now about linear independence. So as we know, any vector it can be expressed using the Cartesian coordinate system as ax I cap plus ay j cap plus az k cap. So the unit vectors, in this case the I unit vector in the case of x coordinate, the j vector in the case of y coordinate, and the k vector for the z coordinate, can be for simplicity can be written as 1 0 0, 0 1 0 and 0 0 1. So we are just naming them as u1, u2 and u3. So if I consider a vector, suppose a is equal to 2i minus 3j plus k cap. So this can be written as also as 3 ordered tuple as 2 minus 3 1. So with the help of these unit vectors, we can express this vector. As we can see here, with the help of the unit vectors, we are expressing this vector. So as we have named them in the terms of numbers, we can also express them as this. So if this is a vector, then we can express it as 2 into 1 0 0 plus minus 3 into 0 1 0 plus 1 into 0 0 1. So this can be written as, if this vector can be called as v, then this is a constant c1, this is the vector u1, this is the constant minus 3 c2, this is the vector u2, and 1 is the constant c3, and 0 0 1 is the vector u3. So this way we can express a vector in terms of the unit vectors. So if I consider the 3 unit vectors as a set S containing the 3 unit vectors, then this vector, the vectors lying inside this set are known as unit vectors, and this set is said to have spanned the whole E3 space. So the number of vectors in the set S is the dimension of the set S. There are two important properties of the set S. The first property is that the vectors inside the set S are linearly independent, and the second one is that any arbitrary vector can be expressed as a linear combination of the vectors of S, that is, as a linear combination of u1, u2 and u3. As we have seen here, we have used the u1, u2 and u3 vector, and we have expressed an arbitrary vector a 2 minus 3 1. So if I have a vector like a equal abc, so I can express this vector using these 3 vectors, 3 unit vectors. So the set of these unit vectors is said to form the basis of E3 space. So as we can express any arbitrary vector in terms of linear combination of S, so it is called the basis of E3 space. So if I have 2 vectors in the set S, and if I neglect this set, then I can say that S is forming a basis of the E2 space. So like this we can go more beyond. Like if I have 4 basis vectors, then I will have E4 space. So okay, after this the set S is said to span all the E3 space. It is like I am just spreading S all over the E3 space, and any vectors in the E3 space can be expressed as a linear combination of the unit vectors present in S. So the next thing is a span. So if I consider a set S as u1, u2, un, this set S is following the 2 important properties, that is, it is linearly independent and any arbitrary vector can be expressed in terms of this vector S. So if I express 2 vectors in terms of S, then v1 can be expressed as c1 u1 plus c2 u2 plus cn un, and also v2 can be expressed as d1 u1 and plus d2 u2 plus dn un. So all the vectors which can be expressed as a linear combination of the vectors present in S are called the span of S. So simply this set S is not strictly to be the set of unit vectors. This can be anything. This can be anything like some different set of vectors like 2 1 1 1 1 1. If they are satisfying 2 important properties, that the first one is that they are linearly independent and any arbitrary vector can be expressed in terms of these vectors present inside the set S. So I have taken a random set S1 which is equal to 1 minus 1 0 0 1 1 and 3 minus 5 minus 2. So let us check if any vector can be expressible in terms of S1 or not. So I have taken a random example, not a random example, an arbitrary example, an arbitrary vector ABC. So let me try to express ABC in terms of these three vectors. C1 into the first vector plus C2 the second vector plus C3 the third vector. So the first equation comes out to be 1 into C1 plus C2 into 0 plus C3 into 3 which is equal to A. The second equation comes like minus C1 plus C2 minus 5C3 equal B. The third one is C1 into 0 plus C2 into 1 plus C2 into minus 2 equals C. So from the first equation what I have is that C1 is equal to A minus 3 C3. So I have just expressing C1 in terms of C3. So from the third equation I have C2 is equal to C2 C3 plus C. So I am expressing C2 in terms of C3. So what I have done, I have just expressing the other constants in terms of one constant. So I have just expressed C1 and C2 in terms of C3 and have put it these values in the second equation to get a relationship between the constant A, B and C. So not constants, they are vectors of the A. So after putting the values, I have get A plus B is equal to C. So what does it signify? So it signifies that if I have to express any arbitrary vector in terms of these vectors, then one property has to satisfy, that is A plus B is equal to C. Otherwise they are not going to be linearly independent and we cannot express any vector in terms of the vectors present in S. So if I have two vectors, say this and this, so let us just consider the first vector only, 1 3 and 4. 1 3 and 4. So here 1 is A, 3 is B, C is 4. So the addition of 3 plus 1 is 4. That is, this condition is satisfied. So this can be expressible in terms of S1. Also, if I have taken 1 3 5, so the addition of 1 plus 3 gives me 4, which is not equal to 5. So this condition is not satisfied. So this is not expressible in terms of this unit vector, S1, the set S1. So if I have a set of n vectors, that is u1, u2, un, and they are the vectors in the space V, and if these vectors are satisfying this linear equation, then I have 0 on the left hand side. So if this equation is being satisfied by this set of vectors u1, u2, un, only when all the constants c1, c2, cn are independently 0, then the vectors u1, u2, un are linearly independent. But if there are also solutions, if c1, c2, cn are not 0, then I can say that the vectors u1, u2, un are not linearly independent. They are linearly dependent then. So from the last example, what I have seen is that when I have got that A plus B equal to C must be satisfied to express any vector in the set S1. So it means that all the vectors in the E3 space cannot be expressed in terms of S1. There are some certain vectors which can be expressed, which satisfy the equation A plus B equal to C. So S1 is not going to span all the E3 space. It is not going to from a basic. So let us take an example. So if I take two vectors 1 0 and 0 1 in E2 space, let me check if the vectors are linearly independent or not. So if they are linearly independent, they must satisfy the linear equation as this. So C1 plus C2, C2 is into 0 and C1 into 1 is equal to 0, and C1 into 0 plus C2 into 1 must be equal to 0. That is C1 equal to 0 and C2 equal to 0. So these two vectors are satisfying this linear equation only when C1 and C2 are 0. Any other values of C1 and C2 does not allow these vectors to satisfy this equation. So the only trivial solution in this case is C1 and C2 to be independently 0. So the vectors 1, 0 and 0, 1 are linearly independent in this case. So I have taken another example, s equal 1 minus 1 and 2 and minus 2. So I have to put these vectors to satisfy this equation. So C1 into 1 minus 1 plus C2 into 2 minus 2 is equal to 0. So from here C1 plus 2C2 is equal to 0, and minus C1 minus 2C2 is equal to 0. So C1 is equal to minus C2 and C1 is equal to minus C2. So these are same. So what I have seen here is that if I take some value of C1, then I will get some values of C2. So not only the trivial solution, that is 0, C1 is equal to 0 and C2 is equal to 0, is being satisfied here. Any value of C1 and C2 are being satisfied here. That is, if I consider some other values of C1 and C2, let me consider C2 as 1, then I will have C1 as minus 2. So let me put this in equation this. So C1 is minus 2, 1 minus 1 plus 1, 2 minus 2 is equal to 0. Let me check if it is 0 or not. So minus 2 plus 2, 2 minus 2. So I am getting 0, 0. So they are going to satisfy this linear equation. So they are also forming a non-trivial solution to this equation. So these two vectors are not linearly independent, as they also have some non-trivial solutions for C1 and C2 other than the trivial solution, that is C1 equals 0 and C2 equals 0. So this is how we are going to check if the set S is linearly independent or not. If the vectors are linearly independent, then this set is going to linearly independent, and if they are not, then So with this, I am just concluding my lecture today. Thank you.